Hello guys, welcome to a fun video, and this video is going to be about how we can approximate or actually compute derivatives using rates of change. And I think this is a very great idea for when we're learning about certain rates, like delta y over delta x. I'm going to actually go over that for a fun thing. But let's just get into it. So one of the things I want to compute is, okay, that's just garbage. I'm sorry. I want to compute f of x that is equal to x squared as a derivative. I know the derivative because it's probably the most rudimentary one I know. 2x. There you have it. And yeah, that's it. So that's how we take the derivative of that. And then the derivative of like a problem like maybe just x would be f prime of x is equal to 1. Because what we're doing is we're moving 1 to the front. We subtract 1 to get 0, and x to the 0 has to become 1. So that's why we get 1. So it just becomes 1 if x is by itself. Alright, but yeah, I'm going to try to take the derivative of this without knowing about the power rule, just algebra. So we're going to need something called a limit, and the limit that we want to use is when it goes to 0, because if it is 0 then we get our derivative, but otherwise we don't. So unfortunately with rate of change fraction problems we are actually unable to get that 0 we want. So we're going to just set a variable h to equal maybe 0.01 for our example's sake. And we're going to go over rate of change. And I'm going to show you a linear rate of change. This one you learned in pre-algebra. And the variable that I'm mostly interested in right now is just that guy right there, m. M is the slope. And we knew that as y2 minus y1 and x2 minus x1, right? And we're actually going to use this concept right here to figure out what the derivative is. So actually in pre-algebra you could have been doing derivatives this whole time. Sorry to bust your bubble. But obviously it would take a long amount of time, and I'll show you why. I'm going to use a calculator to explain why that would be unreasonable. Alright, so let's go ahead and just do it. So first I'm going to set my y2. I want my y2 to equal just x squared, okay? And I want my y1 to equal x squared, but minus that small nudge, that small change. And actually what we're going to have to do is we're going to have to do x minus h and put the power on the outside. So I apologize if that caught you off guard. Yeah, you need to do that. So there's our y1 and y2, and believe it or not, if we took our x2, which is just x, minus our x minus h, well, we'll actually get h back. So all you need to do is just make your delta x equal to h. Okay, delta x is the triangle symbol is used for a change of some kind of rate, and this one's not gonna be crazy. So there's our y2 and y1, and now I'm gonna go ahead and build the thing we need. So we're gonna need some kind of fraction, okay, and we're gonna put our y2 minus that y1 over this, and we're done. So this is approximately equal to f prime of x. Approximately equal means that it will become that if you make h closer and closer to if you make h closer and closer to 0, you'll actually single out some numbers, and that'll help you determine what the answer is, by the way. by rounding. So let's go ahead and plug this in the calculator, and I'm going to expect the graph to become 2x because of the rule. Alright, so let's go ahead and do that. I have good old Desmos. I used a derivative calculator to do some experimenting because I needed to refresh my mind too, but I wanted to share how useful this average rate of change problem can be. So let's go ahead and put 2x right there. And for now, I'm just going to unmark it because I don't want to see it yet, but we'll see that it overlaps in a second. Alright, so the first thing we're going to need is x squared because that's our y2. And then our y1 was x minus h. We'll add a slider. That's the nice thing I like about Desmos. So it'll be great for showing you this example over the x2 minus x1. There you go. And we said we'd set that limit to point that. And you're going to notice that when I go to 2, when x is 2, or not when x is 2, I'm sorry, better example, sorry. When x is 1, can I actually do that? Yeah, we'll do that. We'll do x equals 1. Why not? So look at that. It's 1.99. And 1.99 is very close to this. And watch this. Look at that. Those lines nearly overlap. So if you kept pushing this out further and further and further, eventually you're gonna just you're literally just gonna converge to 2x. And that is why the power rule works. Actually. Very cool, huh? I thought that was really neat when I first saw it too. It's really nice. So yeah, and look at that. Actually, if you keep pushing it out, sometimes the calculator makes errors and says that you've got like, that's probably actually true. By the way, this is probably right. But you can see that it starts singling out to 2. Like I can keep pushing these zeros hopefully. And it becomes 2. See, becomes 2 because it rounded up. All right, so that's the deal with that. So now how do I take the derivative of a more complicated polynomial? Like, I'll show you. I'll show you what we're going to do for our complicated polynomial. Sorry. Limit goes to 0. H equals 0.01. All right, so I'm going to show you another example just so that you can see that this is indeed how you calculate a derivative, or how the rules and such are found, sort of. So right now I'm just showcasing the power rules, and that's kind of what I'm doing. X cubed plus x squared plus x. This is a very nice thing I can show you guys. So that'll be our y2. Now I'm going to show you our y1. It's going to be a little bit more complicated, but you'll see what it'll become. So if we have x minus h to the cube, that's not a 3, there's a 3, plus x minus h squared plus x minus h. That's going to be our y1. And guess what? Our delta x is the same as h. Okay, so there we go. So we've got our y1, we've got our y2, and now I'm going to plug it in the calculator, and then I'll show you how to use the power rule to get the actual derivative of this function. Alright, so let's go and do it. This should actually be very easy to plug in your calculator. Yeah. So let's go ahead and do it. I got rid of h, of course. Of course. So let's go ahead and get our x. Yeah, we're going to need some parentheses. X to the third plus x to the second plus x to the first, of course. I'm going to put it to the first so that you can see it visually. It's an unwritten one. And now we're going to do x minus h to the third plus x minus h to the second plus x minus h to no power, but I'll say to the power of 1. Why not? It's for the sake of the unwritten one. And it looks like I messed up my parentheses. Hold up. Let's fix that mess. There we go. That's a very big problem, isn't it? It's a very large problem, but I can remedy this here. There you go. That's better. So if we add a slider and I make our h limit to 0.01, then this is actually going to converge to that derivative we want. It'll become, as I keep doing this parabola will become that derivative. I'm going to get rid of this fella in a second. Let's go ahead and just change this to, what shall I change it to? I'm going to change this to be our function, of course. Sorry. My mind is not, I'm not smart, so it takes time for me to think. So there you go. There you go. So we got our derivative, and now I'm going to go ahead and show you what the actual derivative is. So we move 3 in front, we decrement that, so it's just 3x to the second. Oh, this is so fun because we get to see it do weird stuff. And then it's going to be 2x to the first, all right, plus 1, because as we've gone over before, that's it. And look at that. We did the power rule, and we got the answer. Check that out. They're basically equivalent if you keep pushing h closer and closer to 0. It singles out the answer. It's very nice that way. I like how that works out. So, yeah, there you go. So we've computed a polynomial derivative just by setting h to a very big value. This is the basic concept of this whole situation. Alright, so what else can we do? Well, there's something else we can do. Obviously doing this by hand is stupid. That's why you do the power rule. We saw this visually, you see. That's a great thing. Alright, so we've gone over that. And now I'm going to go over trigonometric functions, because some trigonometric functions are very fun to compute. Very fun. So let's go ahead and do one of my favorites, cosine and sine. Love them. So we don't actually need to know what the sine and cosine is right now. We're just going to use the function on Desmos, but this will prove the whole point that I'm trying to make with this whole thing. So I know the derivative of sine already. It's cosine, and the derivative of cosine, it goes to minus sine. And I'm going to show you. I am going to show you that this is the truth. So let's go ahead and do it. Let's do it. I'm going to do the derivative of the sine. So f prime of x is equal to d over dx. So this is the derivative in respect to x, and then we're going to throw our sine in there, and we're hoping that we get an answer approximately equal to the cosine, and it will go to the cosine. And there's another way we can supplement this issue as we figure this out. So I'm going to go ahead and put a fraction here. That's not a fraction. Let's use an actual line maker, shall we? There we go. Now that's a fraction right there. Oh, that's beautiful. So we're going to go and put the sine of x as our first y. This is y. This is y2. Okay, it's y2 minus the y1, and we want a small nudge, so I'm going to just do 0.1 for now. Okay, just for example's sake. Sine x minus 0.1. I don't know if you could see that. I apologize, but you get the idea. Over h, and this will be approximately equal to the cosine. So now I'm going to go ahead and plug this in Desmos, as I've done before. So let's go ahead and put the sine of x minus the sine of x minus h. We don't even have that set up yet. And we'll go and make it 0.1. Boom. There it is. Almost a cosine, and I'll prove it. Cosine x. There you go. And watch this. As h approaches 0, gets closer and gets closer and gets closer. And it's the cosine. There you have it. Woohoo! So there you go. That is why the derivative of the sine is the cosine function, without making it super complicated. Because we're just taking this arbitrary change problem, making it more instantaneous. Okay, so I'm going to show you an equivalence to the cosine of x so that you can use this as some kind of shorthand. Let's try that. Boom. There's your derivative of, there's your derivative right there. It's just sine x plus pi over 2. I just did a phase shift. A phase shift is when we just shift the cosine or sine function like this on the horizontal axis. And if you simply do this, you get it, which is quite nice. Alright, so we've gone over that. I'm going to keep h this time. Now we're going to go over the cosine, but it's really not going to be that fun because, well, I've already shown you. So let's go ahead and let's do it. F prime of x equals d over dx. Boom. Get those brackets out and throw in your cosine. Alright, let's do the derivative of this function now. I cannot wait. It's going to be fun. And this should give us, it'll be approximately equal to minus sign, but then it becomes equal when we push it closer and closer to 0. Okay? Let's do it. So, what we have to do is we have to do cosine x minus cosine x. You probably want to put it around parentheses too, or else it just won't work. Minus h over h. Oh. And there it is, approximately f prime of x. Alright, let's go ahead and do it. I'm going to make h equal to 0.1 again. Alright, so yeah, I know I could have just replaced the sine with cosine, but whatever. Minus h, okay, over h, and I'm going to go ahead and make it 0.1 for now to prove the point again. Okay, and let's put the sine function down. Now, see, this is a positive sign. This is why we get negative sign as our result. If I put minus sign, then they'll nearly overlap. Now, as h approaches 0, they slowly converge to minus sine of x. And that is why the derivative of the cosine is minus sine. That's it. That's really cool, but here's the nice thing about this. We actually can get the derivative without actually doing the that rate of change. We can just do a good old phase shift. Let's see if I got the right one here. Now that isn't the right one because what we actually have to do is add this. There you go. Perfect. That's it. So if I do that, you can see that they overlap. So that is basically equal to that, if you want to do it that way. And I think that's good enough for now. That's your basic understanding of derivative or average rates of change. But you know, we put them in the in this kind of way. All right. Thank you for watching. Like, subscribe. I probably might I'm thinking about building some kind of calculator in Minecraft that actually computes derivatives. It's, because it actually is possible. I just have to make a big enough, yeah, I'll probably make a huge register. Yeah, I'll do it. I might do it eventually. Obviously not now, I'm quite busy, but I'll keep that in mind. Alright, take care.